In this example, we will determine the potential due to a ring of charge. Now, our ring of charge is the same as what we had in our previous example where we looked at the electric field due to this ring of charge. So this is set up such that the x-axis goes through the middle of the ring. The ring has some radius r, and we will start by looking at some small segment of the ring which has charge dq. This small segment of the ring is a distance r sub I from a point on the x-axis which we will call point P. So we can determine that the distance from this small, tiny little segment of the ring is x squared. That's the distance along the x-axis from the center of the ring to point P, plus capital R squared, the radius of the ring, all of that square root. Now, as a reminder, for a point charge, potential is equal to 1 over 4 pi epsilon naught times the charge on the object of the point charge over the distance away. So the distance between the point charge and wherever you're evaluating the potential. So we'll utilize this sum up of all of these little tiny pieces all the way around to determine the potential at point P due to the entire ring of charge. So we'll start by using sums. Then I'll show you how to do this using integrals as well. So if we're going to look at small segments and sum over all of those small segments, then the total potential at point P due to this ring of charge is going to be the sum of the potential due to each one of those individual segments. Plugging in for the potential due to a point charge, each individual segment is small enough we can assume that it is a point charge. Each one has a charge q, and it's a distance r sub I away from point P. I'll go ahead and plug in for r sub I. Now looking at this, the only part that we need to sum over is delta Q. That's the only part that's changing as I move around this ring. X will stay the same because the ring is perpendicular to the x-axis, so every point on the ring is the same distance x away. Every point on the ring is the same distance r from the center of the ring. So I can rewrite this pulling out my constants. And I only need to sum over delta Q. Now, if I go through and sum over all of this, the tiny amount of charge for every piece on this ring, I will end up getting the total charge on the ring, which we'll call Q. So then I find that the total electric potential at point P due to this ring is this. Now if I go through the same procedure to do this using integrals, then everywhere you saw a delta Q before, we'll now be using dq. So my total potential will be the same constant in the front times the integral of dq over r, where r is the distance between point P and any segment on my ring. I'll plug in for r, which is the same as our Ri before when we were doing this with sums. That can be pulled out just as it was before. So I'm left with an integral of dq. This is going to go from 0 if I don't integrate over any. If I'm looking at none of the pieces, the charge on that would be 0. If I go through all of the pieces, the charge will be q. The integral of dq from q to 0 is just q minus 0, so q, leaving me with the same result that I got with the sums. So two different methods to get to the same result. Lastly, I'm going to show how you can take the potential and work backwards to get to the electric field. So we already calculated the electric field due to a ring of charge in a previous example, so you can go back, take a look at that one again, and I'll show you a different way to get to this time starting with the potential. So now we're going to find the electric field at P from the potential. Now, due to symmetry, which we talked about in the previous example, I can tell that the electric field is only going to be in the I hat direction. In other words, it's only going to be in the x direction. This is due to symmetry, that everything on the positive y-axis is also in the negative y-axis, so they cancel, so there's no electric field in the y-axis. So I can focus solely on the electric field in the x direction. So to calculate the electric field from the potential, it's going to be negative the partial derivative in the x direction. Now, if there was components in other directions, we would need to continue this and do the partial derivative due to each one, but I already know that these are 0, so we'll ignore them for now. Plugging in for my potential, which we calculated just above, I have this. I can go ahead and pull some of my constants out here. Since we're now taking the derivative with respect to x, q becomes a constant. It doesn't matter what the charge is. And I'm going to rewrite my denominator here in terms of an exponential. So the negative means it's on the denominator, the 1/2 means it's a square root. If I go ahead and take my derivative now, I'm going to use the chain rule. So the derivative ends up being the exponent times the quantity in the exponent. We subtract another one, so now this is the negative 3/2, and now I need to take the derivative of what's inside, which is here, and that's going to be 2x. Again, this is all in the I hat direction. My 2 cancels with my 1/2. My negatives end up canceling. I have 2 negatives, that makes it positive. So I can now rewrite this, taking the quantity in the parentheses and moving it back down to the denominator. So you'll notice that my negative sign up above, now that it's in the denominator, has disappeared. Now it's a positive sign in the exponent. And if you go through and take a look at ring of charge example, you'll find this is exactly what we had previously calculated. The only difference is that what we're calling R in this example was equal to A in the ring of charge example. We just had a slightly different name for the radius of the ring. So that's how you take the potential and determine the electric field.